In this class, we are going to learn three-phase square wave inverter. Similar to the single-phase square wave inverter, the half bridges in the three-phase square wave inverter are also driven by the 50% complementary PWM signals. In order to get a balanced output voltage, the phase difference of the driven signals between each leg is 120 degrees. With such a rule, a repeated sequence of switch vectors is formed. The 101 vector is followed by 100 vector, and then 110, 010, 011, and 001 vectors. Each switch vector lasts for 60 degrees. With the inductive load, there will be a diode freewheeling process at each vector section. For example, at the 100 section, the switch in the lower leg of phase C is turned on, but the current flows through the diode due to the positive inductor current of phase C. The energy is fed into the DC bus. The inductor current and the inductor voltage has different directions. The phase current is gradually reduced to zero. When the phase C current crosses zero, the diode in the lower leg of phase C is blocked. The current is through the antiparallel switch. In the view of small time scale, it absorbs the energy from the DC side, and at the same time, it also feeds the energy into the DC side. There is bidirectional energy flow. However, in the view of large time scale, the energy flow from the DC side to AC side and realizing the inverter function. According to the circuit theory, in balanced three-phase circuit, the voltage of phase A is 1/3 of the difference between the line voltage VAB and VBC. With a similar method, the phase voltage of phase B and phase C can also be calculated. The phase voltage waveform for three-phase square wave inverter is the alternate staircase waveform. In each circle, there are 6 stairs. Therefore, it's also called 6-step inverter. With the Fourier series expansion, the phase voltage can be decomposed into the DC component and the harmonic components. The RMS value of the fundamental phase voltage can be derived as this, which is about 0.45 Vs. The line voltage gain is about 0.78. Comparing with other three-phase inverters, the square wave inverter has the highest line voltage gain. However, the output voltage distortion is serious. It contains a lot of low-frequency harmonics. The orders of these harmonics are 6K plus 1 and 6K minus 1, and the amplitude of the output voltage is not adjustable. Let's deploy the PocketBench real-time simulator. First, connect the DSP launchpad to the interface board. Then connect the interface board to the PocketBench. Finally, use the USB cable to connect both launchpad and PocketBench to the computer. PocketBench can simulate the power converter in real time. When the controller injects PWM stimulus to the PocketBench, it will receive the voltage and the current response in real time, just like being connected to the real power converter. In this class, we are going to do the experiment for three-phase square wave inverter. In the theory course, we have already learned that the three-phase square wave inverter are driven by the square wave interleaved by 120 degrees. And in the DSP, these square waves can be realized by using the phase shift function of the EPWM module. Okay, now let's take a look at the program. In this program, the clock for the EPWM module is 6.25 MHz. We'll explain how to realize this clock in the PWM electronization function. Each PWM module includes 2 PWM channels. So for three-phase inverters, we need to electrolyze 3 PWM modules. So there will be 6 PWM channels. So here the EP-1 module is used to drive the half bridge of phase A, and the EP-2 module is used to drive the half bridge of phase B, and the EP-3 for phase C. In the EP-M module initialization function, the initial fundamental frequency is set to 100 Hz, and since it's a square wave inverter, so the duty cycle is 0.5. And the dead time for the inverter is set to 10 microseconds. All three PLM modules has similar settings. They are all operated in the up and down counting mode. And they have the same period. By setting the EP-M clock div to 1, and the HSP clock div to 2, and the CLK div flag to 2, the clock of EP-M module is set to 6.25 MHz. And all three EP-M modules are operated with the same clock. They also have the same comparing behavior. If the counter is counting down, and when the counter equals to CMPA, then the output of channel A will be set. If the counter is counting up, and when the counter equals to CMPA, then the PLM output of channel A will be cleared. And all three PLM modules are all operated in the complementary mode, and their dead time are set to 10 microseconds. The difference for each EP-M module is in the phase shift setting. So here EP-1 is used as the reference. For EP-M2, its phase shift function is enabled by setting PHSEN flag to 1. The value of TBPHS is TBPRD multiplying with 2 and then divided by 3. So it's 120 degrees. The PHS DIR flag is set to 0. So according to our menu, if the PHS DIR is set to 0, the counter will be counting down after the TBPHS is loaded. So considering these two lines of codes, the phase difference between EP-M2 and EP-M1 is 120 degrees. For EP-M3, its phase shift function is also enabled, and its TBPHS value is also TBPRD multiplying with 2 and then divided by 3. But the PHS DIR flag is set to 1. So according to the menu, if the PHS DIR is set to 1, then the counter will be counting up after the TBPHS value is loaded. So considering these two lines of code, the phase difference between EP-M3 and EP-M1 is negative 120 degrees. So by setting the resistors like this, we can get the three-phase square wave pulse interleaved by 120 degrees. And in the interrupt routing, we calculated the TBPRD and the CMPA value dynamically, so we can change the output voltage frequency in the expression window when the controller is running. Okay, next, let's start doing the experiment. First, deploy the program to the DSP. Then start the controller. Okay, so the initial output frequency is 100 Hz. So next, let's start the PocketBench software and load the three-phase inverter profile. Okay, so here we choose three-phase grid-tied inverter, but we set the amplitude and the frequency of the load AC source to 0. So the load only contains the inductor and the resistor. The line inductance is 2 mH, and the line resistance is 0.5 ohms. The input power supply is 100 volts. Okay, let's start the simulation. Then in the scope, we can see the stair waveform of the output line voltage. First, we need to check if the DSP can generate the 3-phase pulses interleaved by 120 degrees. So let's measure the period of the output voltage. So in order to make the waveform stable, we can use a trigger. Okay. So put the trigger here. Okay. Okay, now let's measure the period of the waveform. Okay, so the period is about 10 milliseconds, and the output frequency is 100 Hz. So it's just what we have set in the DSP. Next, let's measure the phase shift. So the phase shift, so the time difference between phase A and phase B is about 3.3 milliseconds, which is about 1/3 of the whole period. So it means the phase difference between phase A and phase B is about 120 degrees. Similarly, we can also measure the phase difference between phase B and phase C. So the time difference is about 3.3 milliseconds, which is about 1/3 of the whole period. So the phase difference between phase B and phase C is also 120 degrees. So it means the DSP controller can generate the corrected 3-phase pulses interleaved by 120 degrees for the 3-phase square wave inverter. Okay, next let's check the spectrum. So enable the spectrum analysis and move the cursor to measure a whole period. Okay. So the red bar chart is the spectrum for the output voltage VAB. So in the spectrum, the fundamental component is dominant. And besides the fundamental component, it also contains the harmonics, like 5th order harmonics, 7th order harmonics, 11th order harmonics, and 13th harmonics, and so on. So the order of the harmonics include the 6K plus 1 and the 6K minus 1. Okay, next, let's verify the amplitude of the output line voltage. While in the theory course, we have already learned that the RMS value of the fundamental line voltage can be calculated like this. It's 0.78 multiplying with Vs. So the amplitude of the line voltage should be 0.78 multiplying with Vs and then multiplying with the square root of 2. So let's calculate the amplitude for this case. So 0.78 multiplying with 100 input voltage, and then multiplying with the square root of 2. So the voltage should be about 110. Let's check the experimental result. So in the experiment, the amplitude of the fundamental voltage is also 110. So it means the analytical solution derived in the theory course is correct. For the 3-phase square wave inverter, we can change its output frequency, but we can't change its output amplitude. So we may try to change the output frequency to, say, for example, 200 Hz. Okay, let's measure the amplitude of the fundamental line voltage. Okay, so the period is, 200 Hz. And the amplitude of the fundamental voltage is about 110. So it's the same as what we got when we set the frequency to 100 Hz. So even you change the output frequency, the amplitude of the output voltage can't be changed. So for the 3-phase square wave inverter, the amplitude of the output voltage can't be adjusted, and it contains a lot of low-frequency harmonics. And we'll solve these issues in our future classes. Okay, so this is the experiment demonstration today. Thank you for watching.